We are on page 127. So we're going to give you basically practical tips about volume rendering, discuss when you can do it, when you cannot do it. It all depends on the mesh types. Write some pipelines for VTK, and then I'll demonstrate a couple of toolkits, the Nvidia Index plugin and the Intel Osprey plugin, which make the bulk of the support for volume rendering in ParaView. So pseudo volume rendering to begin with. And I'll refer you to page 218 of the textbook, which you find online, very nice. It shows you the essentials of volume rendering. First of all, VTK Mesh Types. We've seen different types, yet we can do volume rendering with VTK image data, but we cannot do it with rectilinear grid or structured grid. With unstructured grid, it's supported, but it's very slow. So my advice would be probably to resample the data to an image data. So the Cartesian grid like this would be directly supported and would be very fast. Those other two types of grids would not be supported. Yesterday, I gave an example with one student here of doing a volume rendering of a block like this of image data, 1024 cube on my laptop. It's real time. There's no limit to that. So not all mesh types are supported, and the same thing goes with the data type. They're not all of them supported. So for example, unsigned, if your data is unsigned short, or if it is short, one of them is, I forgot which one is not supported, but you have to convert your data. Double length floating point data, for example, is not supported. You convert that to float 32. So you really have to be careful about what you're sending down the pipeline. If with the new version of ParaView, if you use Index, Index will print out to your screen exactly that message. Dataset in double format are not natively supported. So it's converting the scalar format to float. So to avoid that conversion, perhaps you should directly feed it floating point data. That would be a lot more smarter in that particular case. If it's not converted, there's here a nice little Python script which I use inside a ParaView Python programmable filter. Let's look at the detail of this. I use NumPy to be able to get the different characteristics of each of the data type. If I want unsigned short, I would use the II-info from uShort, the type uShort in NumPy, get the max value, get the min value, and I would scale my data to use the full range of the unsigned short. My input would come from my input range would come from this particular line of code where this is the name of the scalar field, meta image in that example. I get the range of it, my minimum and my maximum, and then I use a VTK class called VTK image shift scale coming from the VTK image core module, and I scale my data in that particular way. Using the image shift scale, I can set the output to any type. So here you have the choice to making that the type you prefer. And that makes me think I should probably make this a fully integrated filter now that I think of it. So I'll have to do this as an exercise for myself next week. And then you can ask me for the copy of it. At the end of it, I update my pipeline here, and then I copy it to the output of the programmable filter. This really should be used as a black box. You convert your data if it doesn't fit for volume rendering. So back to pseudo-volume rendering. Pseudo-volume rendering would be done compositing translucent cut planes, which are all arranged in a sequential manner. And what matters is that they are all viewed from the same viewing direction. If you have unstructured grid, this would be a good way to do a cheap volume rendering of an unstructured grid by doing multiple cuts, many of them. I showed you an image of it, I think, already yesterday. This would be that particular script I have copied to the rendering directory on date. So you're welcome to exercise that one. However, if your data is of type VTK image data, and this should be the main focus of our presentation this morning for volume rendering, there are much faster methods, and we're going to go through them. If I go to the little exercise here about volume rendering, right here, I'm going to show you a couple of things. So there is this pseudo volume rendering. You can see here more or less the outline of those slices, and they're all semi-transparent, so it kind of works. It works better if I am perpendicular to the screen, because those slices are in the opposite direction. If I am facing on, you see that the quality, I mean, this is not useful at all, but this is just to show you how volume rendering would be implemented. A real implementation, every time you move, the camera would capture exactly the perpendicular to your viewpoint and would cut all the volume with planes which are perpendicular to the viewpoint. This is why here the picture looks better seen from the profile view. Very good. Now, this data set is of type curvilinear, okay, over here. So if I change my representation, volume here is what implements the volume rendering. If I change that representation to volume, it gives me that error message that it's not supported. All right. So this would be a place where we could resample to image data. Let's actually do it. Resample to image would be right here. I'll just use the basic block like this. See, this is a very rough resampling, okay, because I'm using very low resolution, but at least it shows you that this would actually work. One option to go from the structured grid to an unstructured grid would be to tetrahedralize the mesh. This would make an unstructured grid version of your data, all based on tetrahedra. And the default mapper for this is called the OpenGL projected tetrahedra mapper. It's very slow. This is almost 30 years old, this algorithm. This was developed before we had the graphics card, actually. It's there for historical reason. So the showcase is the video that I showed you yesterday. about the convection in this shear layer. And I'm going to load the data and then show you a couple of things. This is our user interface. And what matters is that we set both the opacity and the color transfer function, and then we need to use very small numbers here. Otherwise, you get a fully opaque picture, which doesn't do the job. So let me load that data. I will clean up here. Okay, there's my slice of data. There's the volume rendering of it. Now it uses the default color, which is this blue and red, which is very, very boring and very unfriendly. And the first thing to do, actually most of the work in volume rendering is defining the proper color and the proper transparency. So I have here saved a particular color map which I use for this purpose. At the bottom of my screen over here, there is the beginning of my visualization here, okay? Now, there are some artifacts. By default, but you see it's real time, more or less. By default, I'm using a certain sampling distance, and that is the important thing to note. That particular number here, the scalar opacity unit distance, is what defines the spacing between all the different planes cutting. So if I change this value, for example, make it twice as big, every time I make it twice as big, you can see that the picture over here becomes less luminous, there's a lot more transparent, okay? Let's change that to, I think, the value which I used for the video, which is 0.12. And now I have this interesting setting here. And as I move the mouse, you can see that it gets kind of pixelated here in the middle. And then when I let it go, I do a better approximation, okay? So this would be my rendering here. Let me make this a little bit bigger. There we go. There is my rendering. So there are multiple ways to implement this volume rendering here. And then the question you should ask is really, how did you come up with those colors and the transparency? Wait a second. There we go. So that's actually where most of the work resides. And this is where you need to have, if possible, a low, not really a low resolution copy of your data set, but a sub-volume of your data set, so you can try many different coloring and transparency transfer function. But we'll see that we can also use some automatic tools to do this. So there is the volume rendering. By default, this is my representation here called volume, and this will use a volume rendering algorithm implemented by Kitware in ParaView, which does recasting on the GPU. That's the default. However, if we go to my menu over here, That default menu is the menu called Smart. So it lets ParaView find automatically the best method available. However, I can change that to raycast only, which would be a CPU-only implementation. I can use the GPU-only implementation, which defaults on my workstation to the smart case. Or else, I can use this last option, which is called Osprey-based. Osprey is a library provided by Nvidia to do volume rendering. Okay, and I've actually done this video using all those different techniques to find out the drawbacks, pros and cons of each of the available techniques, and the results have been published in a paper just last month to summarize my findings. Basically here, if I were to switch to Osprey-based, you would see a difference that, see here, it's quite a bit slower. It's about a factor of 5 slower, but the image quality is the same, and that's really what matters. I go back to my smart, see? Much faster. Here I'm on the graphics card, but the image hasn't changed. So this is actually a very good indication that I can do the same rendering on pitch date, not only on the GPU partition, but also on the multi-threaded, on the multi-core partition of my computer. So if you have also, for example, some laptops don't all have a graphics card. If you have a good CPU on them, you can do already some pretty decent volume rendering by using the software-only version of the renderer. Why? Okay, resume. Now, some details, because the computation were saved as a rectilinear grid, I did not have the possibility to use volume rendering, so I converted that with the resample to image data filter. And because the resolution of the original grid was this funny number here, 257, well, when you do graphics on the GPU, you like to pack your data on powers of 16. It's much nicer. So I resampled to 256 for that exercise. Okay. The third option, so I've mentioned the native implementation. I've mentioned the Osprey implementation. And the third option is this Nvidia Index library, which we have also running here on PitchDate to do hardware accelerated rendering. There's the link to the paper I just published last month if you want to know all the details about this. But basically, some of the compromise we have to deal with are the following. Running on one node with a volume of size 1024 cube, memory consumption, first of all. So this is a volume of 1 gigabyte, yeah, more or less. If you have a scalar field, which is floating point data, you have exactly 4 gigabytes of data to move to your GPU. Well, the consumption of memory on using the native renderer or the index renderer is more or less the same. There's index uses a little bit more memory, but that's not a problem. But however, this tells you something very important. The memory on the GPU side will be the limiting factor. So if you're thinking of rendering a large, for example, 10,000 cube volume, you could not do it on a single GPU, okay? Because that would just exhaust the limit of memory on the GPU side. The advantage of the Intel Osprey CPU solution is that you can use fat memory nodes, for example, and really use all the available nodes on your compute, all the available memory on your compute node. Furthermore, there is something that was done very efficiently by Kitware in version 5.6 of ParaView. There was absolutely no duplication of memory between the compute side and the volume rendering implementation of Intel Osprey for volume rendering, so that I could use a zero memory copy of my array to the volume rendering on the CPU side. Unstructured grid is supported. There's this specific class called VTK Unstructured Grid Volume Raycast Mapper. I've tried it. The results are not really exciting, I must say. Using that particular class, I had much better luck using the Nvidia library. I have results here in a couple of slides where I was able to do a very large rendering of unstructured data. So let's come to Index. In fact, Index is documented at the following site. We've used the Index here at CSCS for at least 2 years now, and I must say that Nvidia was very supportive, very helpful in helping debug some of the early problems. So again, here you have to be careful with the data formats used. So unsigned car, shorts, floating points are very well supported. Some other data types will be translated before sending them to the GPU. If I go back to my, my data already loaded over here, to use the Nvidia Index volume renderer, you have to load it as a plugin. So here I go to my list of plugins, and I have the Nvidia over here to be selected. I load it. And I have to close completely this window because I loaded the plugin after having created the window. So be careful with that. Not a big problem per se, but the plugin is only visible if it was loaded before creating the window. So I'm closing, reopening the window, making the data available, selecting again. Actually, it's already selected, that's good. And then now I go to the Nvidia Index rendering, and there is the same, again, the same representation of my data set. Now the interface is a little bit different. Nvidia Index will give you some other GUI elements. Some of them are right here. So for example, you can directly select the region of interest in your box. It's scaled between -100% and +100%. That's kind of a funny set of parameters, but let me show you here. Looking at the full grid, if I change here the K dimensions, say I'm cutting it in half. So this could be useful, and it's immediate, as you can see. It's really very fast to limit the volume of data you want to visualize. This would be the first thing to change. You can also change the step size of integration. Here, if I change this to 0.1, you would get a slightly denser image, but here it looks like that parameter did not have a very big effect. You can additionally show a slice through the data, as I'm showing here. So I can get rid of the volume and only show, you see this is one thin slice through the volume. So this gives you also a very good way to debug your color mapping, okay, using the slice. And then when you're ready with when you're happy with the result, you go to the volume mode, and then you remove that particular slice. There we go. And then finally, there is something very interesting on the Nvidia Index library, the so-called visual elements here. And I'm showing here the menu that gives us 4 different options, which I have documented on the slides, because the example Nvidia gave me was much nicer than I could do. Those visual elements enhance the perception of the volume in different ways. So the default is none. The second option is the Isosurface option, which really is more like an ISO volume. It will make anything below a certain threshold completely transparent, and anything above that threshold semi-transparent. So I'd like to call this an ISO volume instead of Isosurface. And then there is depth enhancement. Depth enhancement will allow you to give more focus on the regions of space where there is high gradients. So let me show you an example of it in the next slide. And those next 3 slides use images that Nvidia directly sent to me, and I didn't bother recreate them because they were done very, very nicely. The first option is enhancing depth cues. This is our original, and perhaps here with the light on the screen, it's not so clear that one is an improvement here. But this is with enhancing the depth cues in that model. The second one is highlighting silhouette on the data. Here we have kind of a very fuzzy regions of space, whereas over here we can actually distinguish some different particle elements that were put in. The final option being the gradient option, where with gradient turn off, we have this particular image, very dark, and then with the gradient turn on, we highlight those regions of space where the gradient is maximal. So this is very nice. Now, those techniques will apply with more or less efficiency. It really depends on the data set. What I'm saying is that I will not apply the same settings for a medical image data set that I apply for this simulation of a galaxy, and each case will be different. The same case I used for the shear layer simulation, I was actually not able to use those techniques very efficiently to make something better, to improve the quality of my images. Talking about medical imaging, here's the data set that I was able to visualize with Index. I converted, this was done strictly as a benchmark exercise because medical data is not usually of type unstructured. So this is based from a CT scan based on a tetrahedralization of the volume, which created 770 million tetrahedra. And in real time, using PitsDaint again, on 64 GPUs, I was able to do that movie of the volume rendering of this particular data set. All right, so as I mentioned, the column map and the transparency transfer function is where most of your work is going to be in trying to highlight features in the data. So sharing this column map is an important feature of ParaView, and it's actually pretty simple. We have a menu to save the column map over here, export the column map with the opacities, and we export that as a JSON file, which is then very simple, very lightweight, to send to somebody via email to do the same rendering on their remote site. So this is what I use, both to share the column map with somebody else, but also here to reload the column map which I want inside ParaView. We can also do volume rendering of isosurfaces in ParaView. There was a nice blog article introducing this feature, I think already a couple of years ago. Now, traditionally, when you want to do visualization of isosurfaces, you generate a polygonal mesh model representing the surface points where that threshold is met, which means you have to create a geometry and then you send that geometry to the GPU. Using this new technique, this new visualization feature, instead of sending the geometry to the GPU, you send that threshold to the GPU, and the GPU via a CUDA program actually does exactly the on-the-run or on-the-fly generation of the geometry. So I have an exercise that does this, and I have an example, I believe, on the next slide right here. This data set, I'll have to verify that I copied it over to PitsDaint, is the result of a Gaussian simulation. So a Gaussian simulation gives us the electronic density in this volume of data. There is the molecule that you can see here immersed into this cloud. And I've selected in this view two different techniques to get more or less to the same result. This should let us appreciate the difference. Here, I'm using the contour value with two different isosurfaces set, and those isosurfaces are made semi-transparent. On the left side instead, I use this particular feature of the volume renderer with the show isosurface flag turned on, and I gave it the same isosurface threshold available. And you'll see that the pictures are slightly different, but they're both very useful. One of them has the advantage that there is no geometry explicitly created for this particular rendering. So let me see if I can demonstrate that in real time, and then you'll have also that example to play with. I just forgot which one. Which one I did, but I will do this. I will load my data over here. So there's my Gaussian data set. It only shows the atoms. And I would have to use a module to compute the molecular bonds I have to use something else slightly bigger, I believe. There we go. So there's my molecule. When you use ParaView for molecular data, there's a special mapper that does the cylindrical and the sphere-like representation typical to molecular data. This is a GPU mapper. So it basically, as you can see, there's no more choice over here available to change points, wireframe, surface. No, there's no, all of those options are disabled. And by default, this GPU mapper, which is specific to molecular data, is used. So here I'm just increasing the size of my molecule a little to make it a little bit bigger. All right. With the Gaussian data, there is a second output on the reader, which is the grid itself. Okay? So if I take this grid data and do two isosurfaces like this, this is what I would get. Okay, let's not worry about the colors for the moment. This is the electronic density function around this molecular data. And of course, I don't see very much because one isosurface covers everything else below it. So I can make it semi-transparent, going like this. Okay. I'm starting to have something more useful, but still I would have to work on it. And the problem here is that doing the correct rendering of semi-transparent polygonal surfaces requires a feature which is enabled in ParaView by default called depth peeling. So depth peeling is this possibility to have, for sure here the choice of color is very bad. Let's see if I can make something better that's not really obvious. Okay, all right, fine. So here we have generated the iso contour. I'm going to switch that, turn this off, go back to my grid data, go to the volume rendering of the grid data, and as you can expect here, my density volume shows like this. And some of your work, for example, is going to be to eliminate all this outside region here. This is the region that is right here at very low density. This is how you would work with the opacity transfer function. As you can see, I have here the option to modify my opacity transfer function. Okay. So this really is something that you should do interactively. You cannot really improvise that rendering. And if I exercise that last feature of the renderer, which is to show isosurfaces, I'm going to add the same two isosurfaces I had earlier over here. I now have this volume rendering of the isosurfaces, and it's done it's very high quality. It's much better than the polygonal display with semi-transparent rendering. As you can see here, we get a really good idea of this electron density cloud surrounding the atoms. Okay?
I have a question.
Yes?
I'm confused between the difference between contouring, like the surface contouring, and the volume rendering.
Well,
They do look the same.
yeah, exactly, and that's the point. They should look the same. One of them, this is the volume rendering of the isosurfaces. Instead of creating a geometry, I do a recast on the GPU side of the volume cloud, and I intersect my ray, if you want, only with those values in the volume which meet the criteria of the isosurface. So there's no physical geometry, there's no triangles which are generated. The classic, the old style method was to create an isosurface filter, to create geometry, and then send that geometry to the GPU to be rendered as a normal triangular module object. But this has disadvantages in that to do proper polygonal rendering of semi-transparent objects, you need to have this algorithm called depth peeling, which only does an approximation of the rendering. So this is of higher quality. Let me go back to the same object using the contour. There should be some artifacts, and if there are none, I can make them appear. Settings, render view. I'm going to turn off the depth peeling. Okay. Is that clear that there are some artifacts here? If you focus on particular areas, it's not clear at all exactly. It's not clear at all where, if one surface is in front of the other. Okay? I'll try not to change orientation here. And I'll go back over here. We have a cleaner implementation of this transparency. Because what we do here, we really traverse the volume, and as we traverse, we intersect the cells with that particular threshold of data. So I recommend using that for this type of molecular clouds, density volumes. I recommend to use that technique of isosurfaces rendered directly on the GPU. Now, there's more than that we can do with volume rendering. Let's take, for example, a particular volume of data, which I have made a copy of it on pitch date. We can look at it during our exercise. If I look at a histogram of the data, I see 3 peaks of intensity in that volume. Further, if I look at the magnitude of the gradient, I see a high peak here with the low gradient, and then I see a gradient that goes all the way to about 150. And what I like to do, I like to separate, I like to remove all the data with low gradient, because low gradient usually means there's nothing much happening. And I like to focus on the high gradient volumes in the data. And if I do this, with this particular example, which is a scan of a tooth, this is what I get. This is the regular volume rendering, and this is the volume rendering with the gradient opacity turned on. And as we see, we find here exactly those 3 peaks of intensity, which corresponds to the what they've done a root canal. There's here the ceramic, and there's here the how do you call it, the dental work that was done. So those are the 3 different intensities of my tooth, and by removing the regions of space with low gradient, I'm able to see exactly the silhouette of the internal structure in the data. Well, how is this done in ParaView? The answer is you cannot do it in ParaView because ParaView does not give you access to this particular function of the volume properties available in VTK called set gradient opacity. So this is a Python code which I have prepared for you to run with PV-Python on your own laptop, and the details are over here. If you recall this particular function which plots the magnitude of the gradient, right about here at 50, this is a value I have decided more or less arbitrarily. I set up an opacity function which goes from 0 to 1 and then 1 everywhere else. What does it mean? It means that all the data in this range over here will be completely transparent, and then from here on I will have that rendering. So this is my gradient function. It's a piecewise function starting at 0, going to 50, always 0, and then going to 100. So this is a ramp from 50 to 100. We have a ramp going from 0 to 1, and then everything else is 1. And then I set 3 different functions. The scalar opacity, which is the normal opacity transfer function, which we also have in ParaView. I set the gradient opacity function, and then I set the color transfer function. And with those 3 functions together, I get my rendering. So there is the demonstration of it. And I'm pretty sure I have copied it over already to PitsDaint. Actually, yeah, this is the script which loads the data set. So here's the tooth on the left side. Over here, it calculates the histogram, and on the third window here, it calculates the magnitude of the gradient. Okay. And that reminds me that somebody asked me about doing more analysis on data. How would I compute the gradient of the data? Well, there is a calculator in ParaView. This is the user interface for the calculator. And right over here, in that particular window, I don't know if you can see, if it's not too small, I've written mag for magnitude of the image gradient. So basically here we have a number of elementary, we have like a small calculator, you know, like those hand calculators we used to have, or like you have on your cellular phone, where you can do some simple arithmetic expressions using the name of the scalar field. So what is important here is that my source of data, if I look at the information, it has a field called meta image. That's the name of the scalar field of type unsigned short. That's intensity, yes. That's basically the intensity of the scan. I've calculated the gradient, and the gradient gave me a field called meta image gradient. And now to simply evaluate the gradient of it, I do mag of meta image gradient. This is one way to do some simple arithmetic expressions. There is the trigonometric expressions, the dot product, etc. And then if you want to do more, you can use the Python calculator itself. The Python calculator itself, I did not have time to present it yet. I could probably do it at this time. In the filters, you will find and the P, the Python calculator. The Python calculator has a very simple user interface over here, an expression. You select if you want to operate on the vertices or on the cell data. You select the name of the array that you want to prepare, and then you are free here to write a single expression that can be as complex as you want using all the NumPy functions that you know of and all the algorithms from the NumPy algorithms package of ParaView to define an expression. So I could here, it's a little bit cryptic in the sense that it doesn't give you access to the names of your scalar field, of your vector fields, etc., in the same fashion as the calculator here. If I go back to the calculator, you can see here that I have a pull-down menu for scalars and for vectors. I can select my vectors where the names of the scalar fields are already there available. Those names are the same names you would use in the Python calculator, but there's no user interface for it. I recommend you read in the ParaView user guide the chapter on the Python calculator, and that is very useful. You'll see that you can really do a lot of operation on it. All right, so this is with ParaView, this little script. However, although we see a little bit of the transparent structure here, we have not removed those low gradient regions in the data. That's because we can't. The graphical user interface of ParaView limits us to to the available features here and does not give us the capacity to set a gradient opacity transfer function. So we do it with VTK. We do it directly with the VTK toolkit instead, and I just have to find the correct data, which I believe is here. There we go, yeah. That's the one, okay. So, I need to do it in the following way. I will show you the code. This is the code I have put in the slides, by the way. So the definition of my piecewise linear function for the gradient. So 0 from 0 to 50, a linear ramp from 50 to 100, from 50, oh no, well, okay. I'm looking in the wrong place. There it is. Zero opacity from 0 to 50, a ramp from 0 to 1, between 50 and 100, and then 1 until the maximum value of the gradient. And then the volume property is, for gradient, is disabled by default, and then I will enable it during the interactive session. So I run PV-Python, and then I execute that particular file, like this. Okay. There's my interactive view. If I now change my volume property, disable to be off, I haven't refreshed the screen here. Now you watch, as soon as I move my screen, there we go. The gradient opacity kicks in, and I now have this almost transparent volume rendering of the data. Okay? So the color coding is to be honest with you, I don't remember what the color coding is. I think it's pretty basic. The main focus of this demonstration was to show you that I can eliminate the low gradient regions of space. So the little catch is that you cannot do this directly in ParaView. You have to do this using the VTK level Python. So the syntax is slightly different, but as you could tell, I'm running this still from the PV Python executable, because it turns out that what is important is the following here, is import VTK, and by default ParaView does import VTK, okay? So there's a couple of things here I wanted to highlight as well. It's those two modules. In VTK, you have an interface to the NumPy arrays so that you can take a VTK data array and use it as a NumPy array, and vice versa. So it's very flexible, and this is why here at this point I can also import NumPy, linear algebra, and I import the norm, and I will compute right here the gradient as the norm of the density gradient, and the density gradient comes from this algorithm package which is provided by the VTK NumPy interface. So I would need a whole hour of lecture to give you details about this, but the message is you can mix and match NumPy and VTK arrays. You can interchange from one to the other, which means you can inherit all the very strong mathematical support available in NumPy directly in ParaView. This Python calculator, which I have very quickly mentioned earlier, this Python calculator uses the NumPy syntax. So this is the way how you could do some pretty strong analysis of your data, selection, feature selection, query, etc., using NumPy, all of this within the ParaView environment. So there is this. Here I have commented out the matplotlib text, which I use to generate the two images in the text. That example is also copied onto Dane. So you're welcome to take this and exercise it as well at home. And back to the color transfer function, you were asking me, see, it's pretty simple. Piecewise function with 4 different points, 0, then this is grayscale, and this is grayscale again, and then at the end we have an R. This is red, green, and blue. We have a major component here for the red component. This is why our picture looks gray everywhere except red at the very top. And those values over here for the 4 different key points of the color transfer functions, those values correspond more or less exactly to those different peaks of intensity in the histogram. This is why I was telling earlier, to do volume rendering, you can try different things. If you know some specific features about your scalar field, if you use a histogram, if you use other analysis technique, then you can focus your attention on those particular scalar values. Yes? Yes, for this, you can find it. Over here. Undained, in Scratch. There is the tooth script for ParaView. There is the tooth data. So the tooth data is using this MHD format, okay, which tells us the size of the grid, the type, and this is compressed binary data, and that file is available as well over here. This is the tooth data. There is the script for ParaView. Over here is the data set for the Gaussian output, which I have demonstrated. And this is the script PV-GPU Isosurfaces. This is the script to use to do the rendering of the isosurfaces on the GPU. So those examples are there to work with those data. Okay? And I guess what I'm missing is the one to use for PV-Python to do the Gaussian, to do the gradient opacity elimination in VTK, and I will copy it right over now. So it's that data, it's that script which I will copy now to date. Okay. And basically, I have finished here the description of volume rendering, and now it's only for you to try. And if all of this is too complicated, ParaView has an application running inside your web browser called ParaView Glance. So if I make an example of it, yes, I know, it's asked the internet. I'll have to verify that that link, but if it doesn't work, we can ParaView Glance. We can search for it. We can install it as a package, or there's also, actually, if I go to the example here, I thought they had examples directly there. Yeah, the two dataset is right there, by the way. Thanks for showing it to me. There used to be an example directly on the website, which I can't find right now. Gallery.
Take off the /gallery and put /app.
Very good, thank you. Why did it not show up? Oh, there it is. So visualize your data with ParaView Glance. There it is. So there's my tooth. There we go. And there's my data. All of this inside your web browser. So you see the interface is slightly different now. We have here directly embedded into the interface the histogram of the data, and then you're welcome to play with the transfer function here. See, I can make the tooth disappear completely. I can change the size of that data, scale those intensity. It's a very fun tool. I've used it also on my cellular phone and makes a nice impression. The problem is you can't save a script out of it, so it's difficult to take once and then replicate at another time. All right. So this concludes the discussion about volume rendering, and then I had prepared those examples for you to, they're really examples, they're not exercise, because doing volume rendering is pretty involved, it takes quite a bit of time. I want you to run those examples to see them working on your laptop, and then to get confidence with the use of volume rendering for your own data. Okay? So we'll stop here. So yes, you can import data into the interface of ParaView Glance. but it has to be pretty small because you're importing that over into your web browser. I've tried it with the datasets I was interested in, and it just broke. Okay. Sébastien Jourdain is the person at Kitware who is responsible for this. He's done a remarkable job, by the way, at doing all those different tools. ParaView Glance is one of them. All the VTK JavaScript stuff is done by himself as well. This is interesting. I mean, if you had a small version of your data set, this would be something easy to share with somebody away at a different site, sharing via the web. Sharing what again? Okay, good.